If you're a fire protection engineer, you know just how critical a building's standpipe system is. I mean, it is the building's firefighting backbone. So in this explainer, we're going to break down the essential design principles from NFPA 14, which is the standard, and see how it lines up with codes like the Saudi Building Code or SBC. Let's jump right in.
So, here's what we've got on tap. We'll start with system classifications, then get into the nitty-gritty of flow and pressure. After that, we'll tackle how to handle high pressure, talk about riser layout and hydraulics, and finally, we'll tie it all together with a practical high-rise design example.
Before you can calculate a single thing, you have to answer one really fundamental question. Who is this system actually for? And that, right there, is where classification comes in. It's the what that's going to define everything else you do in your design.
First up, the Class I system. This is the heavy hitter. It's built for one group and one group only, professional firefighters. That 2.5-inch connection is the high-powered tool they absolutely need to attack a serious fire.
A Class II system, on the other hand, is all about that immediate, first line of defense. Think of it as the break glass in case of emergency setup for trained folks inside the building. The smaller 1.5-inch hose is way more manageable, and it's designed to let them control a small fire before it really gets out of hand, buying precious time until the pros show up.
And then you've got Class III, which is basically the best of both worlds. It gives you that heavy-duty connection for the fire department and the more accessible station for the occupants. This combination offers the most flexibility, and honestly, that's why you see it in so many different kinds of buildings.
Okay, so we know the what. Now let's talk about what the system actually has to do. This section is all about the required flow and pressure. These are the two non-negotiable performance numbers that you're going to build your entire design around.
Here it is, the first magic number you need to know, 500 gallons per minute. This is the absolute minimum flow your system has to deliver to the single most hydraulically demanding standpipe. And what that really means is the one that's highest up and furthest away from the pump. Every single calculation you do starts from this baseline.
But what happens when you have more than one standpipe? Well, NFPA 14 keeps it pretty simple. You start with 500 GPM for that first riser, and then you just add 250 GPM for each additional one. The code is smart though. It knows you're not going to fight a fire from every single stairwell at once, so for most buildings, the total required flow is capped at 1,000 GPM.
And now for our second magic number, 100 PSI. This is every bit as critical as the flow rate. This is the minimum pressure you need at the outlet of that highest and most remote hose connection while that 500 GPM is flowing. This makes sure that firefighters have enough oomph to create an effective fire stream, even at the weakest point in the whole system.
Okay, so we know we need 100 PSI at the top, but this brings us to a huge engineering challenge, especially when you're talking about high-rise buildings. See, to get that pressure all the way to the top floor, the pressure at the bottom floors can become absolutely enormous, just from the sheer weight of all that water sitting above it. So that raises a really important question. How high is too high? At what point does that pressure become just unmanageable, or even flat-out dangerous for a firefighter trying to hook up a hose?
And NFPA 14 gives us a very clear, hard and fast answer. 175 PSI. If the pressure at any hose valve, and that's static or residual, goes over this limit, you are required by code to install a pressure-reducing valve, a PRV, to knock it down to a safe level. And let me tell you, choosing the right PRV is just as important as knowing you need one in the first place.
So this really creates two different ways to approach your design. For shorter buildings, you can often get away with a PRV-less system, where the pressures just naturally stay below that 175 PSI line. But once you start getting into high-rise territory, usually over 12 or 14 floors, a PRV design becomes absolutely mandatory. You have to do it to manage those pressures safely.
And the physics behind this is really simple. For every single foot of height, a column of water gives you about 0.433 psi of pressure. As a building gets taller and taller, that number just adds up fast. It makes pressure management one of the main things you have to solve in any high-rise design.
All right, now let's get into the how. In this section, we're going to cover the physical layout and the hydraulic calculations that turn all these rules and requirements into a real working system. This is where the rubber really meets the road.
NFPA 14 gives us some really clear, straightforward rules for the physical layout. You need a standpipe in every required stairwell. That makes sure firefighters always have access. You've got to have hose valves on every single floor landing. And your fire pump has to feed directly into this system. It's a really logical, robust setup when you think about it. Now, the calculation process itself, you can really break it down into 4 logical steps. First, you figure out your total required flow based on how many risers you have. Then, you calculate the pressure you need just to beat gravity. That's your static head. After that, you've got to account for all the pressure you're going to lose to friction. And finally, you just add it all up to find the required pressure for your fire pump.
And that third step, friction loss, is where this industry-standard formula comes into play. The Hazen-Williams equation lets you calculate exactly how much pressure gets lost as water is rushing through all those pipes. It's an absolutely critical piece of the puzzle for sizing your pump correctly.
All right, time for our final section. Let's take all these principles and put them into action with a real-world high-rise design example. This is where we'll see how all these numbers and rules really come together.
So, picture this. We've got a 20-floor tower, and it has 2 standpipe risers. Our first step is to calculate the total flow. Easy enough. That's 500 GPM for the first riser, plus 250 for the second one, giving us a total demand of 750 GPM. We still need that 100 PSI minimum at the top, and for this example, let's just estimate our friction and device losses at about 25 PSI. So the core calculation here is pretty straightforward. We need 100 PSI at that highest hose valve, plus another 25 PSI to overcome all the friction losses. That gives us a target of 125 PSI. Now, the key thing to remember is this is the pressure the pump needs to deliver at the elevation of that top valve, and that's before we even add the static head needed just to lift the water that high.
Think of this table as your design cheat sheet. It really summarizes the core formulas we've been talking about: how to calculate total flow, how to figure out pressure from height, how to find your required pump pressure, and of course that simple 175 PSI rule for when you need PRVs. Mastering these is really the key to any good standpipe design.
Look, a solid grasp of these NFPA 14 principles isn't just nice to have, it's essential for any life safety design. So the real question is, how are you going to apply them to make your next project even safer and more compliant? Thanks for tuning in.